All right, well, let's talk about decision trees. And these things are very nice, very easy to understand. Um, and we'll talk about what they do and then some details about how you would regularize them and fit curves with them. Decision trees are incredibly simple. It's just a series of if statements. So it's very fast to run and very easy to understand. If you don't like what it does, you can easily read the code and figure out what to change. And you can make them more powerful by making a lot of decision trees and making a random forest where you combine many of them to cancel out their errors. So if you want to train and visualize it, it goes like this. If you think about that flower data we had for irises, where there were petal length and petal width could be measured, and by using those, you could separate it into the three species marked here by colors. So the first question is the length less than 2.45? If that's true, you go here. If it's false, you go there. And here, there are three categories. Originally, you had 50 of each of the three species of flower, but after this one if statement, you've got all 50 of the ones in this class Setosa separated, so you're done. You have completely sorted the data with one if statement. But the two remaining ones overlap somewhat. So now you go to the width and decide if the width is less than 1.75, and you end up with an imperfect separation. This one here is almost pure, 45 of one species and only one of the wrong species. And over here you have 49 of the right species and 5 of the wrong species. So with two if statements, you've gotten a pretty good separation. And this number called Gini is a measure of the disorder. So if Gini is 0, you have perfectly categorized the data where there's nothing in this box that's the wrong category. And as you can see, this is Gini of 0.5 because you have a 50-50 split between two categories here. And down here, your Gini gets much smaller, down to 0.1 or 0.04 so your goal is to make Gini small as you go through these if statements. So now you can make predictions, which is incredibly simple. If you have an example, just the petal length is 3, so this is true. Petal width is 2, so this is true. So that's it. All you have to do is two if statements to get to the answer. So once you've got one of these things, they run really fast. So here you have the number of samples. That's the number of train instances that this node applies to. And then the value is the count in each class. So this is the original starting condition with 50 samples from each of three classes. And that's called Gini impurity. And this is the mathematical equation for it. It's 1 minus the probability of for over all the samples, the probability of this sample being in that category, I think, cubed. So it's 1/3 of each of the probabilities. That's how you get 2/3. Don't see why you need, okay, right. GI is the Gini impurity. This is node number I. So K is the important thing. These are the probabilities. All right. So here's decision tree boundaries. So here you can draw it if you have petal length and petal width. The first decision was here. And as you can see, being to the left of that gives you complete accuracy in determining these. Being to the right of that gives you a mixture of these. So the next one is to cut it this way. And now you get a pretty good separation, although not perfect, of the greens up here and the blues down there. And if you continued, you could have another depth equal 2 lines here where you had yet another separation here to try to fix the errors of the previous decision. So this is a white box model. It's interpretable. And that's very different than neural networks we've talked about before, where you have a lot of hidden nodes, and the hidden nodes have combined information from many of the inputs, and you really don't exactly understand what each of those nodes is doing. All right, so you can estimate, you figure out the probability that this thing is actually Virginica, if you categorize something as Virginica. And so to get an idea of how accurate it is, you can just say 45 out of 46 of the samples here are Virginica, so it has a 98% chance of being right. That's one way to measure the success of the model. All right, and so here's an algorithm called classification and regression tree. First, you split it on a single feature and a threshold t, and you can find values here that produce the purest subsets weighted by size. So you choose the parameter to use, and you choose the threshold to get the most separation between the categories in each step. And this is the mathematical cost function for that. So it splits the root node that contains all the data, and then it splits the subnodes, and it stops either when it cannot reduce the impurity anymore, or it has reached the maximum depth. This is what's called a greedy algorithm. At every single step, it tries to maximize the value of this step. So it is not capable of using more complicated strategies where you might get temporarily worse and better later. It just always tries to get the maximum purification out of every step. So the computational complexity is very good since you are splitting half and half and half. If you count the total number of leaves in the tree, it is of the order log 2 of n, the number of steps you have to do. So if we go back and look at this tree here, you see I have 1, 2, 3, 4, 5 leaves, but it really only takes 2 decisions to get there. So if this kept splitting, there'd be more and more in every layer, but the number of steps it would take to use the model would go as the logarithm of the number of categories, a number of boxes here. So that's very fast and very good. That's the computational complexity. Now, training is n times m log n, where there's n training instances in your set, and n classes, of course. Training can take more calculation, but once you got it trained, it's really fast and easy to use. All right. So also, if you know your computational science, there's this thing called Shannon entropy, where you take the probabilities of various values and you take the log of them and calculate this quantity. That's another measure of impurity, and it amounts to, in practice, about the same thing. You could use this instead of that Gini impurity, and you'd converge to pretty much the same answer. Now you can think about regularization, because you can overfit with decision trees just like other models. Now, the other models we've used, like linear or polynomial, they have a certain number of coefficients, a certain number of parameters you're adjusting. Those are parametric models. Decision trees don't assume anything about the shape of the data. They don't assume it's a straight line or a curve or anything. They just make if-then statements to split it in half, and they can grow as complicated as needed. So you can overfit. So here's your hyperparameters. You can limit the maximum depth. You can limit the maximum number of features, maximum leaf nodes, and other things. You can limit the allowed complexity of the model. And you can also do pruning. You could first train it without restrictions and then prune it, deleting unnecessary nodes. If you decide that that node doesn't really have a significant effect, that's another way to get there. And so here, if you have no restrictions and you're trying to separate this curved set of red dots from these green dots, then it will actually create this, where you have this complicated shape here, and then you have a group of stuff down here that you interpret it as light yellow instead of orange, and a group up here that you interpret it as orange instead of yellow. So it has enough if statements to create this complicated non-contiguous boundary. But with regularization, you could limit, for example, the number of samples per leaf, where it's not allowed to split any smaller than having 5 samples in leaf nodes, which will limit the depth. And now you get a regularized answer where it has a contiguous boundary, orange on this side, yellow on that side, which is probably more representative of the underlying data. So it's the same as other things. If you don't have regularization, it will fit the data and the noise, and therefore be a less useful model because it doesn't really reflect the trend of the phenomenon you're measuring. And then you can do regression. You can fit curves with it if you want to. Instead of predicting a class, it predicts a value. And what that looks like is this. You have a shape here you're trying to fit, and it's just going to fit it with a bunch of horizontal lines. So it's going to give a sort of analog to digital approximation of this. And if your depth is limited to 2, you'll only have this many values. But if you go to depth 3, you can have finer steps. And that's the game. It'll evaluate anything, but it will always be as a series of straight lines. And here's the mathematical expression of that error bar. I don't think it matters that much. And here you can do overfitting with no restrictions. You could fit the data essentially perfectly by just having many, many if statements, so it spikes every single point. And that, of course, is ridiculous. That is not the real trend of the data. So limiting something like don't give me any leaf nodes that have less than 10 dots in it, that gets you a much better approximation of the shape of this curve. All right. And then, of course, remember the other ones had a serious sensitivity to scaling one axis. This one has a sensitivity to the orientation of the axis. If you have this data, it can nicely draw this line, but if you rotate it through 45 degrees, it's going to take more leaves and be less accurate because the if statements only work on one parameter at a time. So you can only have horizontal or vertical lines. You cannot have diagonal lines. So that's an issue here. Rotating your data might make it less effective. Now there's a principal component analysis transformation, and this will reduce the correlation between the features. We'll use it extensively later to lower dimensionality, where you find which combinations of parameters have the most predictive power. And you keep just those and ignore the others to make the problem simpler. And that often helps with decision trees. You carefully choose axes that are extremely valuable. So if you have a rotated thing like this, you wouldn't use this axis or this axis as the most effective one. You would create a new input that's something like x1 plus x2 or x1 minus x2 that would give you a line like this as a natural line. And that's what principal component analysis does. It combines, rotates the parameters in parameter space essentially to choose directions that are most useful for prediction. And clearly this is the most useful thing for prediction along this axis here. All the blues have a low value of this, and all the reds have a high value of this. So that would be a principal component. And that's what you have with principal component rotation. You now, this one you can do with, you're able to rotate the problem so that all these vertical lines are good at separating it. And all you need is a single feature now. This combined feature Z1, which combines both width and length of the petal, is something where that one parameter is a pretty good job at separating all the categories. All right, now decision trees have a high variance. If you make changes in the hyperparameters of your data, you might get very different models. Even just repeating the fit with a different random number seed can give you a different model. So you often make a forest where you don't make just one decision tree, you make a forest of many decision trees. And that turns out to be one of the most powerful models. Just combining a lot of these decision trees together and averaging them makes a pretty good model. And so here I am retraining the same model. First time I train it, I get this match we saw before. The next time I train it, we got this one. Remember, you could do it this way. You could use the petal width to pick these off entirely, and then it would be the petal width used here. So, these are two decision trees that are both approximately equally valuable. They have approximately equally good job of separating the categories. And if you had several of these using different parameters like this and average them together, you work even better. And that's a random forest. So that's decision trees.